Hello and welcome to ML with AP. This is the second video of the series where we are discussing support vector machine. If you have not watched my previous video, the first video of the series, I highly recommend you to go ahead and watch it. This video will make much more sense if you have watched the first one. So what we have learned till now, we have seen the maximum marginal classifier. In the last video, we also saw the intuition behind the soft margin classifier, aka support vector classifier. We have seen the complete math work behind it. Now in this particular video, we are going to see something which is super important, which is support vector machine and the kernel trick. So without further ado, let's jump right in. Okay. Till now, we have seen this particular thing. This was the loss function with L1 regularization where we stopped our previous video. Okay. Now, this is all good, okay, because the data was linearly separable. But what if the data is not linearly separable? Nobody guarantees you that with a straight decision line boundary, you can separate the data. In real world, data doesn't occur like that. So does support vector classifier work on that or doesn't work that? Let's try to answer. Let's try to see it with an example. On the left side of the picture, we have a unidimensional. On a single line, we have it's a binary classification on unidimensional. Only one feature is there, which is x1. We have a square, which is blue colored, and we have a triangle, which is green color. Now, friends, tell me, is it possible to linearly separate this? If we draw a straight line over here, linearly separate that, drawing a straight line. If we draw a straight line, there will be misclassifications about this. If we draw a straight line over here, there will be misclassification about this. So there is no way with these type of data is called non-linearly separable data. So what is the solution? Support vector classifier or maximal margin classifier will not be able to help in this. What we need to do is something called support vector machine. And how do we do that? Let's try to see the figure on the right. Okay. Intuitively, and this we have done if you know about feature engineering, then we do a lot of data transformation as part of feature engineering. Think it like feature engineering. So what do we do in feature engineering? We create new features and we do the transformation on the existing features or the existing columns. Here we have created a new feature called x2. So from unidimensional, I'm mapping this particular data set into a two-dimensional space. And what is my second dimension? My second dimension is x2. And how I got x2? x2 is nothing but x1 square. If I'm squaring all the data inputs and storing that into a second variable, which is x2, and then I'm plotting x2 versus x1, this is how my data is going to look like. Clear? Again, to repeat that, from unidimensional, I'm making it two-dimensional. I'm mapping it into a higher dimension, just like we do into the feature engineering thing. What we did, we have created a new feature x2, which is nothing but the square of x1. Okay, when we do the square of each of these data points, this being on 0 0 0, it will remain on 0, right? X2 will also be 0, and similarly these data points, the x2 value will be, these are very close to 0, so it will rise a little here. The data points which are further away from 0 will rise higher on the x2 plane, right, on the x2 axis, and hence this thing will get mapped into this particular two-dimensional space. And now if we have to linearly separate, we can see easily and intuitively that there is a line which can separate linearly the square with triangles, right? Between a square and triangle, we can easily draw a dotted line over here which will linearly separate the data. Okay, so what is the takeaway over here? If the data is not linearly separable, you have to do certain transformation, okay, to make it linearly separable, and you have to port your data into a higher dimension space. What? We are porting it from one dimension to two-dimensional space. Using what? Using making a new feature, doing a feature engineering with squaring of my original feature. My original feature was x1. I'm squaring it. I'm getting a new feature. I'm plotting it in two-dimensional. Now I am getting it a straight line which can cut it. Okay, let's see it with another example, and this will do it from 2-dimensional to 3-dimensional. Figure on the left, if you see, can you ignore, please ignore the line over here, this line for now. If the data is something like that, do you think the data can be linearly separable? If I draw a line like this, no, there is a huge data over here. There is no way we can linearly separate this data. This data on the left is in 2 dimension, x1 and x2, right? What if I transform this data into a higher dimension, again doing the same technique, and then plot into 3 dimension? Okay, now this 2 dimension to 3 dimension mapping, I have done it like this. My x1 is the new, on the left hand side, this is the new features. This is the old feature, existing feature. So my x1, the new x1, capital X1, will be a small x1 square. Okay, I'm creating 3 new features out of 2 features like this with this mapping, and then I'm plotting it over here. So friends, can you see my x1, x2 and x3 over here? x1, x2 and x3 new feature over here. Now in this 3-dimensional space, can you see that the data have become linearly separable? In 3-dimensional space, when it was 2-dimensional space, all we needed was a line, okay, to separate it. In a 3-dimensional space, what we'll need? We'll need a plane. And if in n dimensions, we'll need what we call it as a hyperplane. Okay, so friends, always remember the plane or the hyperplane which will separate the data in a higher dimension. If the dimension of that higher dimension is n, over here let's say 3, the equation or the plane which will separate, or the hyperplane which will separate, will be n minus 1 dimension. Okay, let's take it with an example. Over here, how many dimensions we have? 3 dimensions. And how many dimensions will the plane will have? The plane will have a 2-dimensional space, right? Which will linearly separate it. Let's see it over here. You see the plane over here in the gray grid. This is a 2-dimensional plane, right? And how many dimensions we have? We have 3 dimensions. So 3-dimension space can be bisected, or can be the decision boundary will be 1 less dimension. So 3 dimension was there, 1 less dimension is 2 dimension. So we got a 2-dimensional plane. We can only visualize till 3 dimensions. Humans can't visualize 4, 5 dimensions. But trust me that what we call them is that hyperplanes. We cannot visualize with our eyes, but we can imagine that in a nth dimension space, if I have to separate my data into 2 sections or 2 groups, I have to use a hyperplane with dimension n minus 1. Similarly, over here with 3 dimension, the plane which is separating it is 2-dimensional plane. If there are 2 dimensions over here, the line which is 1 dimensions, right? The line is y is equal to mx plus c. We are separating it with 1 dimension, 1 less dimensions. Okay, friends, I hope this is clear. Now, one more thing is, this is a projected dimension, right? We are projecting our 2-dimension figure into 3 dimension, okay, by creating features x1, x2 and x3, capital X1, capital X2, capital X3, okay, and then we are separating that out with a hyperplane, in this particular case a 2D plane. When we project this back into 2D, when we do a reverse transformation, at that time my data which is linearly separable in a higher dimension will look like this. It will all be curvy. It will not remain linear in a 2-dimensional space, right? So this particular thing, when it transported back into 2 dimension, it will look like this over here, okay? But what support vector classifier or support vector machine cares about, that what it is doing is, it is porting it is transforming it into a higher dimension. And in that higher dimension, there is a n-1 dimension hyperplane which will be able to linearly separate the data. That's the gist, that's the crux of it. Okay, so if you have understood till this point, you have understood what SVM is doing. Now, just to repeat, what SVM is doing, it will transform the features into a higher dimension, let's say nth dimension, and in that n dimension the data will be linearly separable with a hyperplane of n minus 1 dimension. Clear? And when we port it back to the original dimension, it will not remain, my hyperplane will not remain linear. It will be all curvy and wavy, okay, as we can see. Okay, now one thing is there that we have to project it to the higher dimension, and in higher dimension it is linearly separable, all good and fine. But the question which will come to anybody's mind will be how to figure out which higher dimension is right for a hyperplane to linearly separate the data. That why we have to do it to 3 dimension or 4 dimension or nth dimension. How do we determine that, right? That is one question which will come. And the second question will come, do we, like how we do for feature engineering. In feature engineering, friends, if you recall, we actually transform the data. Do we actually transform the data and project into or just project into a higher dimension? Do we actually do all those calculation and computations to transfer it into a higher dimension? Now the answer for both the question lies in kernel, okay? And kernel is short for kernel function. So it's nothing but a function, treat it like a function. We are just going to see it in detail. Okay, so what is SVM kernel functions or kernel? Let's see it. So friends, when we, in the last video when we were discussing, we were seeing the data was linearly separable, right? If the data is linearly separable, that is the first case, SVM will work great. You use the kernel linear and SVM will work great, right? Because the data in its existing dimension itself is linearly separable. Let's say the data is almost linearly separable. There are some data which are outliers, some data which is coming on the other side, right? SVM can still make it work using SVC. If you recall in the last video, what we did with the L1 regularization, okay, and we tweak the value of C hyperparameter, which is L1 regularization, and with that we are seeing that, okay, my margins will be thinner or thicker, the road will be thinner or thicker, right? But I will still be able to linearly separate the data. There will be some misclassifications, but I will gain on generalization, right? So there was a bias variance trade-off, which if you recall from the last video, we discussed that in detail. Okay, so if the data is almost linearly separable also, we can do with in the existing plane itself, right? We can do with hyperparameter C, and we can see the generalization, bias variance, and all those things. Let's say in the existing dimension, the data is not at all linearly separable. What we have seen just now, okay, in the previous slide. What we can do, SVM comes in over there. What we do is we project the data into a space which is higher dimension. We don't know which dimension is that, but we know it's a higher dimension, okay? And over there in that higher dimension, this problem becomes the statement number 1. It becomes linearly separable. In that higher projected higher dimension, the data becomes linearly separable with, let's say that higher dimension is n, then n minus 1 hyperplane should be able to linearly separate the data. And that's what the kernel does. Okay, clear? So what's the issue? There are 2 issues. One is combinatorial explosion. Let's try to understand this particular with a Excel sheet. Okay, over here what I've drawn is, let's say this is the existing number of feature, my column B. Okay, this is my new feature, this is my existing. Let's say I have a 3-dimensional data set, right? 3 dimension, 3 features. If I'm doing a polynomial kernel, like me, I'm raising it to the power of 2, 3, 4, 5, 6, 7, 8, 9, then my new feature dimension will be like this. So suppose I'm raising a 3 features, I have x1, x2, x3. Let's say I have 3 features, and I'm using a polynomial kernel, which is I'm like in a higher dimension, I'm raising to the power of 2. My new feature dimension will be 6, right? And this is a combinatorial, right? I've just used the formula over here. So now, friends, you know that in modern data science world, there are n features, right? It's very easy that there could be 20 features or 30 features, right? let's say if we have 30 features and you are taking a sixth power to transform it to higher dimension, you know how much it will be? You know how many new features will be? It is exploding. The number of features will become very, very, very large. And once it becomes very large, it becomes very computationally intensive, and it will not be fruitful. It will just run forever. It will not be fruitful that to transform features like this. Like you have a 30 feature and you are raising it to the power of 6. My new feature dimension will be this. This is like 1 million, 1.6 million or something features, right? And 1.6 million features, even by today's standard, our computers will not be able to handle easily. Probably they will be able to handle, but not easily. You will need GPU and all those things, right? Huge cost. Okay. So friends, with this, I hope you got an understanding that what is combinatorial explosion, which we are talking about, right? So number of features you raise to the power, and the combination is very, very huge, right? The number of dimensions which you will get is very, very huge. That is what I meant by combinatorial explosion. And because of this combinatorial explosion and the number of new features in higher dimension becomes so large that the cost of computation goes very, very high. So that's the issue with it. Is very easy to say that, okay, let's project it into a higher dimension and we'll linearly separate it. But it comes with a cost, and the cost is computational cost. So what is the solution? The solution is a trick which is called kernel trick. Okay. So instead of like how we do in feature engineering, what I was telling you, that you transform the data to higher dimension. In kernel trick, what we'll do is we will map without actually doing transformation. Now, what do I understand? Like, what is this? Like, you'll map, but you'll not do the calculation. What is this, right? Let me explain to you. What I'm saying is that unlike feature engineering, where you actually transform the data, you actually do that fx, h to fx mapping. Over here, what we'll do is we'll do these calculations without actually doing the transformation. And I will try to explain you that what, and that's the basis of kernel trick. So what is a kernel? A kernel is nothing but a shortcut that helps us to do certain calculation faster, which otherwise would involve computation in higher dimensional space. So kernel is not essentially related to SVM itself. Kernel is a generic mathematical tool to do complex operation in a simpler way. That's what it is, right? Let's see it with an example. Okay, let's see, I have defined a kernel. I have two data points, x and y, and this is in my current dimension. X, y are in my current dimension. Let's say that dimension is n dimension. So xy is an n dimensional. X also has n features, y also has n features. That's what it means, right? And I'm doing an operation fx. What this operation is transforming to a higher dimension. What is that higher dimension? Let's say it is a m dimensional. My n is the existing dimension, m is the higher dimension where I'm mapping. And what is that mapping? That mapping is fx. You can treat it as like when I'm doing a polynomial like a square. Then I had feature x1 and x2, and if I'm doing a square of it, what I will get? I will get three features, x1 x square, x2 x square, and x1 x2, right? Three features I will get. Similarly, this is what fx means, right? I'm putting it to a higher dimension, which is m dimension, okay? And this bracket, triangle bracket, if you see over here, this represents the dot product, okay? So I'm trying to find a function, mathematical function, which will do the same thing as performing the dot product of fx and fy. That's what I'm trying to find. And that's the definition of my kernel. So what kernel should be doing? The kernel should be performing the dot product of two functions fx and fy, right? So I'll take two data points. I'll take two data points from my existing n dimension. okay, and then I have to calculate the dot product of them in higher dimension. That's what kernel is. Let me repeat that. What is a kernel? The kernel is a function which will give the output, the dot product of any two vectors in existing dimension, which is n dimension. When these vectors are mapped into higher dimension, which is m dimension, what is their dot product? That's all kernel is, right? And friends, if you recall, dot product is a scalar quantity. So the output of this kernel is always going to be a scalar quantity, right? Now, why we are getting into this dot product and all? It seems, as I was telling in the first video also, dot product is a similarity measure. Okay, so if 2 points, imagine we have 2 points in an n-dimensional space, x and y. They will be considered similar when their dot product would be large. Okay, that means they are facing in the same direction. So x dot y will be what? Norm x norm y into cos theta, the angle between them, right? Between these two vectors. And it will be large. If they are similar, their dot product would be large. If they are dissimilar or not similar, their dot product would be small. And this is what SVM is trying to do. SVM is trying to predict a new feature or a new observation in a higher dimension by doing this similarity measure. Okay, what it will do, if it has to predict a new observation in a higher dimension, it will calculate the dot product, and then wherever the similarity is higher, it will predict that particular class. That's what it is doing. Okay, and hence this dot product of every feature pair or every observation pair is important to calculate in case of SVM. Okay, so kernels are similarity measures, right? Because they calculate the dot product. And why dot product is necessary? Dot product is necessary because we have to gain the similarity, right, between each pair in a higher dimension space. Okay. Let's see it with an example. Okay, let's say x is x1, x2, x3, y is 1. There are 2 points, right, in my existing dimension. This is my existing n dimension. So n is 3 over here. It is a 3 dimension. And there are 2 data points, 2 vectors, x and y. x1, x2, x3, y is y1, y2, y3. Let the kernel be, and I'm using a polynomial kernel with a power of 2, right? Let the kernel be power of 2. What will be the fx? When x1, x2, x3 needs to be mapped to a higher dimension with this square thing, then what we'll get? We'll get x1 h square, x1 h2, x1 h3, h2 x1, x2 x1. All these combinations will get similar what we are saying about the combinatorial explosion. So how many such features we'll get? We'll get 9 features over here. 9 features. So from 3, we arrived at 9 feature. Correct? Understood? Now x was 1, 2, 3, y is 4, 5, 6. Let's say without doing the kernel trick, we have to calculate the dot product. Ultimately, our aim is what? Our aim is to calculate the dot product, right, in a higher dimension. Let's say without doing the kernel trick, we first do the mapping, like how we do in feature engineering. We did mapping. So 1, 2, 3 mapped into a nth dimension will be 1, 2, 3, 2, 4, 6, 3, 6, 9. How it is coming? This is nothing but x1, 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 x2, x1, x3. This is the number. Okay. Similarly, when fy, which is 4, 5, 6 in existing dimension, if I put this into higher dimension, this is 16, 20, 24, 20, 25, 30, 24, 30, 36, right? Clear? Like how we have arrived? We have not done it. It is just a mapping, right? From 1 to 3, we have gone to a higher dimension, nth dimension. Why we arrived at the nth dimension? Because we are using a polynomial as 2, right? Now, if we have to do the dot product in a higher dimension, fx and fy. Fx, fy are in the higher dimension, nth dimension, which is 9 over here, 9 dimension, 9 dimension. If I have to do a dot product, what will dot product be? Dot product will be multiplication of the first term with first term, second term with second term, third term with third term, fourth term with fourth term, right? And we have calculated finally the dot product will be a scalar, which is 1024. Now friends, see, without doing the kernel trick, how many computations we are doing? From here to here, how many multiplication? 9 multiplications we did for x, right? Correct? 9 multiplication. Similarly, 9 multiplications for y also we did, right? 4 into 4, 4 into 5, 4 into 6, all the combinations like this, right? 9 multiplications. So 18 multiplications in achieving fx and fy, correct? Now, when we do the dot product, we did 9 more multiplications, right? Pairwise, correct? So there will be 27 multiplication. 27 multiplication, and finally we had to do 8 additions. So 27 multiplication plus 8 additions to arrive at a single dot product, which is 1024. So if we are doing this sort of kernel mapping or polynomial, which is to the power 2, we have to do 27 multiplications and 8 additions, right? That's the computational cost. Remember that. Let's see, we do the same thing with using the kernel trick. Now, what is the kernel trick over here? Kxy. What we'll do? We'll do the dot product of them, right? In an existing dimension. So what will be the dot product? Again, it is pairwise multiplication. So 1 multiplication, 2 multiplication, 3 multiplications, right? 3 multiplications and 3 additions. And 1 more multiplication because we are taking the square after that, right? So 32 into 32 is 1 more multiplication. So how many total multiplications? 4 multiplications and 3 additions to arrive at the same scalar quantity, which is the dot product in a higher dimension, 1024, right? How much we got over here? We were doing 27 multiplications and 8 additions. Here we have done, instead of 27 multiplication, we are doing 4 multiplications. And now multiplication is the most, this is a simple example, but multiplication is very computationally heavy. Instead of 27, you are just doing 4. And what we are doing? We are not actually, if you see, that's what I was talking about kernel. We are not mapping this into a higher dimension. We are not calculating the fx and fy. We are not mapping x and y into higher dimension. What we are still calculating the dot product in a higher dimension, but without actually explicitly mapping it. That's what kernel trick is all about. And kernel trick, why it is so popular? Because it is computationally very light, right? Instead of 27 multiplication, we just did the same. We achieved the same result with 4 multiplications, correct? This, my friend, is the kernel trick. I have posted a LinkedIn post today, and I have explained this in detail. Probably I will, if you go to my LinkedIn page, you'll see this detailed explanation also over here about the same thing, okay? That what is a kernel trick, and I have given the same example in detail over here. So I will link this in the description, and if you feel like it, please go ahead and read it over there as well. Okay, so this, my friend, is a kernel trick. Okay, with this being said, probably I will take a pause over here for this video. In the next video, we are going to see the SVM code, and we'll code it using SciKitLearn. Till that time, have a great day, and please subscribe to my channel if you have not done so. I'll see you in the next video.